Welcome. Now here we have this model, A of t, which represents the descent of an airplane. T is measured in minutes. And in the last video, we worked out a domain here. And the altitude along the vertical axis is measured in tens of feet. We've labeled where the plane begins its descent and where it has landed, and modified our model to only focus on the descent of the plane. Okay, now let's work this out. Let's work out this average rate of descent from 2 to 7. Those of you in my course on your notes, just go ahead and cross out the number that was there and replace it with a 7. So to find the average rate of descent from 2 to 7, we need to find the slope of the secant line. So it will help us to actually sketch in a line. So please get a ruler and connect these dots from 2 to 7. Hopefully I can do it without it snapping to a weird position. Oh, look at that. Well, it doesn't really want me to connect them that well. Do your best to connect these. I'm going to quickly trace my line, draw my line. And what I mean is draw a line connecting those 2 points. So pause your video and connect those 2 points, please. Okay, as you can see, I went ahead and connected my 2 points with this sort of salmon colored line here. So I connected. This is when t equals 2 and t equals 7. Now this is the secant line. And it's a secant line between, or connecting, to 2,800, so that's 28,000 feet, and 7, 550, which is 5,500 feet. That's what this is right here. We need to find the slope of this secant line. So let's write this down. The slope of the secant line is equal to the average rate of change on this interval. And I'll be really clear. I'm going to draw an asterisk. This is the interval I mean. So from 2 to 7, t equals 2 to 7. Let's go ahead and actually write it out as an interval. So our interval, instead of doing the asterisk there, it's from 2 to 7. There we are. There is our interval from 2 to 7. These points are included. Let's go ahead and find the slope of this line. Remember, slope of the line is the rise, the up and down over the run. Rise over run. It's basically figuring out if we were climbing these steps, what would be the incline of those steps in essence. All right, let's work out our average rate of change now. So the average, and this is from t equals 2. So from t equals 2 to t equals 7, well, that's equal to our altitude function evaluated at 7 minus our altitude function evaluated at 2 divided by 7 minus 2. And as we had already figured out by looking at the graph, when t equals 2, the output is 2,800. That's 28,000 feet. When t equals 7, the output is 550, which is 5,500 feet. So let's go ahead and replace now, instead of a of 7, well, look, this point here, this is 2 comma a of 2. That's what this point actually is. And this point here is 7 comma a of 7 in function notation. So a of 7 is 550. A of 2 is 2,800 here. And 7 minus 2 is 5. Now when we subtract that, in our numerator we get negative 2250, so 2,250. In our denominator we have 5. So this is just negative 450. And now what are our units? Remember, this is in tens of feet per minute. So within the context of this problem, we write this plane is descending or losing altitude at a rate of 4,500 feet per minute. And now I'm going to just quickly touch on two things. Remember, our units are in tens of feet, so we need to multiply this by 10. This is where the extra zero comes from. And for those of you wondering what happened to the negative here, well, I say it's descending. This word here is, in essence, represents that negative. So when I say descending, we're losing altitude. So that's telling us that our value here for our rate of change needs to be negative. If it was ascending, that would tell me that it was positive. Oh, and let me add one last thing here. I didn't say the interval, which is important. I mean, between what time and what time, between how many minutes and how many minutes. So this plane is descending at a rate of 4,500 feet per minute between 2 and 7 minutes into descent. Please keep calm and math on.